So indirect method is only for the simple geometries. Then for the complex geometries, we are going for the direct method. That is straight away we are placing the source sheet and vertex sheet on the profile itself straight away. Okay, this is the second method. So now we will discuss some basics what you have studied in your fluid dynamics. So you know the difference between rotational flow and irrotational flow, right? What is the difference? Rotational flow, rotational flow. Or so can you say which is rotational flow, which is irrotational flow? So here I have done two flow conditions. Can you say which is rotational, which is irrotational?
Sir, both could be irrotational also because free vortex also irrotational.
Both could be irrotational.
Yes, sir. Like because like free vortex is also irrotational.
Okay. Okay, good. Any other? How to differentiate rotational and rotational flows? Okay. Okay, but rotational irrotational flow is not based on the streamlines. It is based on the fluid element. For example, if this is the fluid flow. Okay, so we have infinite number of small fluid elements, right? In the fluid flow, you know it is very closely packed. So we are calling this as continuum flow. But if we go to the edge of the outer space, where the distance between each air particle will be around 1 kilometer. Okay, now in the near to the earth, so we cannot distinguish the distance between two air molecules. But if we go to outer space, there you can see the distance between each particle is the around 1 kilometer. Okay, so if you stand and if you move, you could sense that so one particle first will hit you, and after 1 kilometer distance only another particle will hit you. But near the earth, if you stand, you can see simply the airflow. You cannot sense the individual air particle hitting you. Okay, so within the atmosphere, the air is continuum, but outside it is not obeying the continuum. So this is called rarefied flow, rarefied gas. This is different. What did I say? Okay, so in the airflow, lot of fluid elements will be there. So based on the fluid element motions only, we can say whether it is rotational or irrotational. In both streamlines, if you see, the fluid particles are translating. Okay, it is translating along this curve. Here also the fluid particle is translating along this curve. Extra lines. It's after ritual. So in both streamlines, if the particles are simply translating, that is moving along the streamline, then that is called irrotational. Okay, but if the particles are translating, also rotating, then it is called rotational. Okay, based on this fluid particle only, we have to say whether it is rotational or irrotational. So you should not take the streamline patterns. It can be a curved streamline or straight streamline, but depends upon the fluid particle only. We have to say if the particles are simply translating, then it is rotational. Is it clear? Rotational, irrotational flow. So if it is simply translating, then it is irrotational. If the particle is translating, also rotating, then it is called rotational flow. Okay, that's why in that you said right. In the vortex, the particles are simply translating along the streamlines. That's it. It is not rotating. That's why the vortex is the rotational. But only in the center the particle is rotating. So only in the center it is rotational. Outside streamlines it is rotational. Is that clear?
Yes, sir.
Okay. So here
So can you repeat that?
okay, I'll repeat it. So this is the example. So I have taken flow over the aerofoil. So there will be a bound layer growth, and the velocity profile inside the bound layer, right? So outside, so we will get the free stream velocity, which is constant. Okay, but inside the boundary layer, near the wall, due to the friction between flow and the wall, the velocity will reach zero. Then it will little bit increasing, and it will reach maximum at the end of the boundary layer. Okay, so this type of variable boundary layer profile we will get it inside the boundary layer. After that, it will be constant. So if you take this free stream that is above the boundary layer, the velocity is constant like this. So here also 10 meter per second, here also 10 meter per second. And whatever the particle lies within this region, it will simply translate. Okay, because both sides same velocity, so simply this particle will translate in the free stream conditions, both the boundary layer. But inside the boundary layer, assume here it is 0 meter per second, 1 meter per second, 2, 3, 4 like that. At the end only it reaches 10 meter per second. After that it is constant 10 meter per second free stream. Okay, so inside this boundary layer, there is a velocity difference across each streamline. For example, if you take these two streamlines, assume here it is 1 meter per second, here it is 2 meter per second. So here also the particles are translating, but due to this velocity difference, this particle will rotate. Okay, so if the particle translate and rotate, then this is called rotational flow. And outside, same velocity, particle is simply translating, so it is irrotational flow. Okay, this is the example. So within the boundary layer, particle translates, also rotates, so it is rotational. Outside the boundary layer, it is simply translating, so it is irrotational. Is that clear?
Yes, sir. Thank you.
Okay. And vorticity. What is the term vorticity? You studied, right? What is meant by vorticity? Anybody remember? Okay. So the strength of this rotating
Strength of the vortex, sir.
strength of the vortex. Okay. That is circulation. Good try. That is circulation. Very good.
Yes.
So the strength of this rotating fluid element is called vorticity. Okay. Strength of the vortex is called circulation. You are correct. But strength of this rotating fluid element is the vorticity. Here you can see how the strength is defined. It is based on this velocity difference, right? If the velocity difference is v1, v2 differences increases, this particle may experience what is it? Very high speed rotation. Okay, so the strength is depends upon this velocity difference. So mostly we will denote this by small gamma. Okay, the strength vorticity we are denoting a small gamma, and it is simply due to the velocity difference v2 minus v1. So the strength of this particle is simply the velocity difference. Is that clear?
Yes.
Okay.
Yes,
So
sir.
vorticity means strength of the rotating fluid element. So now we will go to this vortex. So this is the real vortex. So you can see the whirlpool in that lake or wingtip vortices. These are all the real vortex. But we will come to the ideal vortex. So what we use in this potential flow. Okay, this vortex first we'll discuss. Ideal vortex. So it is simply a rotating fluid region. Vortex means, and the streamlines are the concentric circles. The vortex means simply a rotating fluid region. Okay, this fluid region may have n number of fluid particles, fluid elements. Okay, so this is the rotating fluid region, and where the Streamlines are the concentric circles. So all the circles has the same center, and vortex will have only the tangential velocity, and there is no normal velocity. So you know the definition of streamline, right? Streamline will have only the tangential velocity. There is no normal velocity. Is that clear? So vortex means
Yes.
rotating fluid region where the streamlines are the concentric circles, and it has only the tangential velocity. There is no normal velocity. And strength of this vortex is called circulation. Okay. Strength of the vortex is called circulation. We are denoting that as capital gamma. Now, what is the strength here means? The amount of fluid flowing along this line. Based on that only the strength is defined. So vorticity means based on this velocity difference. Okay, if the velocity difference increases, it can experience very high rotational speed. So that is the strength. And in the vortex, strength means amount of fluid flowing along this line. Okay, that means simply a volume flow rate. Okay, the volume flow rate along this line defines the strength of the vortex. And for the ideal vortex, that is theoretical vortex, the strength is constant. At each streamline, the strength is constant because we have taken inviscid flow assumption. The strength is constant. And if the strength is constant, this ideal vortex will not disappear. It will go to infinity distance. Okay. But in the real condition, if you take, so here the flow is compressible, viscous, etc. and all, you can see it is not exactly circle. Okay. It is a little bit distorted and it is not extended to infinity distance. See here itself it is dispersed. Here itself it is start disappearing. Here also you see, you can see the vortex only within this region. Okay, because of the viscous, because of the friction, so the strength decreases outside. Finally, it disappears. But if you take ideal vortex, according to the theory, it should be extended throughout the lake. Okay, because the strength is constant. That is the difference between real vortex and ideal vortex. Is it clear? So in the real vortex, the streamlines may not be the exact circle, and the strength is not constant. The strength will decrease in the radial direction. Finally, it will disappear because the flow is viscous. But in the ideal fluid, we have assumed the streamlines are concentric circles and the strength is constant. So once the vortex is started, it will go up to infinity distance. Like that we assume. Is it clear? Difference between ideal and the real?
Yes, sir.
Yes, sir.
Okay. Okay, now we will find the circulation, that is volume flow rate along this vortex. So for that, initially I'm taking one small arc length dl. Okay, so for this small section, I'm going to find the volume flow rate. Volume flow rate means velocity into area. So here it is 2D structure. So area is dl into unit length. Okay, so the area is dl into 1 simply dl, and tangential velocity is v. So for this small arc, the strength I'm taking as d gamma. The strength is volume flow rate v into dl. Is that clear? So for the complete vortex, the strength is capital gamma. I have taken one small distance dl, where the strength is d gamma, that is volume flow rate, velocity into area, dl into 1. It is simply v into dl. That's what I have written here. And this arc length, I can write it as r d theta. Okay. Assume the radius is r, the angle is d theta, then dl is equal to r d theta. Instead of dl, substitute r d theta. So this is the strength of this small section dl. Now if you want to find the complete strength of the vortex, you have to integrate it from 0 to 2 pi. Okay, 0 to 2 pi we have to integrate it. And if you integrate, this will be theta. Substitute the limit, you will get gamma is equal to v into r into 2 pi. That I have rewritten as v into 2 pi r. So this only you have studied in your fluid dynamics. And if you rearrange, you will get velocity is equal to capital gamma divided by 2 pi r. These two formulas you studied in your fluid dynamics. I don't know whether you studied this derivation or not, but these final formulas you should have studied. Is that clear?
Yes, sir.
Okay. So strength of the vortex is circulation. It is simply the volume flow rate, amount of fluid flowing along the line. Okay, velocity into area. Okay. Then types of vortex also you studied. The first one is free vortex. That is, it is created due to the natural force, gravity force. So you may observe this type of vortex in the sink. That is, if you unplug the sink on the blockage, you can see this type of vortex. See here, they similar using the water bottle. So they removed the bottom cap, and due to the gravity, the water is coming out. In that time, it is creating this type of vortices. It is called free vortex because there is no external force is applied. It is just formed due to the natural force, that is gravity. Okay, and due to the gravity, the water is pulled out. So the velocity is maximum in the center, and it will decrease towards the edges. So if you draw the velocity profile, it is maximum in the center, and it will decrease towards the edges. Okay. So practically, if you see, the velocity at the center is finite, but theoretically, if you see, it will go to infinite. Okay, practically there will be a finite velocity in the center. Theoretically, it will go to infinity. So this is the free vortex formed due to the gravity. So velocity is maximum in the center and decreasing towards the outside. This also you studied, right? Types of vortices.
Yes, sir.
Okay. And next one is forced vortex. So here I have taken the vessel with glass beaker with the water, and if I rotate this beaker, okay, that is by applying force on both sides. If I rotate it, then we can see this type of vortex pattern. Okay, so if I rotate it by applying the force on both sides, I can see this type of vortex pattern. Is called forced vortex because we applied the force on both sides externally. That's why it is forced. It is not formed based on the natural force gravity. It is formed because we applied the external force on both sides, rotational force. Here you see the force is applied on both sides, right? This side and this side, the force is applied. So velocity is maximum at that end because here only we applied the force. Then due to the viscous flow, the viscous property, the velocity is decreasing towards the center. Okay, just reverse. This clear, right? So here we applied the external force, so it is called forced vortex. So here I compared two vortices. For the free vortex, which is formed due to the gravity, velocity is maximum in the center. For the forced vortex, which is created by applying the external force on both sides, the velocity is maximum at the end. Okay, this is free, this is forced. These two you have studied. And Rankine vortex. This is the combination of free plus forced. Example, the real-time tornado, whirlpool, etc. and all. So here you see, due to the velocity difference, this tornado is formed. Okay. So inside region, if you see, okay, due to the velocity region, the tornado is formed. So velocity will be maximum at the edges, and it will start decreasing towards the center. Okay, inside this region, it will be like a forced vortex. So here we applied the force. That is due to the velocity difference only these tornadoes etc. are created. Okay. So here velocity is maximum, decreasing towards the center. So this region is forced. Okay, and here we have the maximum velocity. And outside, due to the friction, this velocity will decrease to this zero. Okay, so this region also you can see. So here it is maximum due to the friction. This velocity will start decreasing. Finally, it will be zero. So that portion is like the free vortex. Okay, outside it will start decreasing and vanishing, and this portion is called free vortex. So what are the natural vortices we see? That and all called Rankine vortex, which is the combination of forced and free. Inside it is formed due to the forces, velocity difference. Outside, due to the viscosity, it is decreasing. So it is like a free vortex. Is it clear?
Yes, sir.
Yes.
Okay, just tornado. What is the sound I'm hearing? Anybody is chatting? Anybody is facing issue? Okay, tornado. So here, due to the okay. So here, due to the velocity difference, it is formed. So inside it is forced. Outside it may decrease. So here also you can see the rotating air. Okay, that is called free vortex. This is forced vortex. Sometimes it can be a single tornado. Sometimes you can see the cluster of small tornadoes. So here they explain the internal structure. So there is a one big tornado. Inside also there will be a rotating streamlines. In that streamlines also there will be a velocity difference, and due to the velocity difference, there may be a small tornadoes formed, vortices formed. Okay, just additional information. It can be a single tornado or it can be a cluster of small tornadoes. The small tornadoes are created due to the velocity difference inside the rotating bigger tornadoes. Okay, so next one is just definitions. This they may ask in 2 marks or 1 marks. The vortex I explained, rotating fluid region where the streamlines are the concentric circles and it has only the tangential velocity. The strength of the vortex is capital gamma. Okay. The next one is vortex filament or vortex line. Both are same, filament or line. That is, if you place n number of vortices in a same axis or same line, that is called vortex line or vortex filament. Okay. If you place n number of vortices in the same axis or in the same streamline, then that is called vortex filament or vortex line. Is that clear?
Yes, sir.
And the assumption is, so these vortices has the infinitesimally small strength. That is, these are all the very small vortices. So it is behaving like a rotating fluid particle. So here I mentioned, right, this is the big vortex and the strength is capital gamma. And here if you take each small vortices behaving like a, that is, these vortices are very small. So it is like a rotating fluid element. That means strength will be like a vorticity. Okay, so each vortex has the small strength of small gamma and overall vortex length strength is capital gamma. Okay, so assumption is, so vortex filament has the infinitesimally small strength vortices. Okay, small vortices, strength also small, very small. So all the vortices behaving like a rotating fluid element. So strength is simply the velocity difference, V1 minus V2 or V2 minus V1. And the overall vortex filament strength is capital gamma. Is that clear?
Yes,
Yes,
sir.
sir.
Okay. The next one is vortex sheet. And if you place n number of vortex filaments side by side, you can get this vortex sheet. Okay. If you place n number of vortex filament or vortex lines side by side, we can get the vortex sheet. So here also same assumption. So each vortex filament, vortex sheet has the infinitesimally small vortex. So each has the small strength gamma, and overall vortex sheet strength is capital gamma. So here they explain. So the side view, if you see, it will be like this. Okay. So this is the top view or some isometric view. In this side, if you look at, it will be like this vortex sheet. Okay. This is the axis of vortex filament. Each vortex filament, but in the side view, it will be looking like this. So each vortex filament has this small strength gamma, and overall vortex sheet strength is capital gamma. And here we found the strength of this vortex sheet. Assume the length varies from 0 to s. I'm taking one small distance ds, and each vortices have this small strength gamma. So for this small region ds, the strength will be gamma ds. That is, the strength is d gamma, which is equal to gamma into ds. You know, gamma is the velocity difference. So velocity into area, volume flow rate. Okay. So I'm taking one small distance ds, and each vortices has this small strength gamma. And for this small length, I'm taking the strength is P gamma, which is equal to volume flow rate, that is small gamma into ds, where the gamma is the velocity difference. Then for the complete vortex sheet, simply we have to integrate it from 0 to s. Is that clear? This one we will use it in the second unit. Vortex sheet strength. Should I repeat?
So,
Hmm.
so you said a vortex filament has the strength of capital gamma.
Yeah. So from here to here, we assume, what is it? So the vortex is very small. So it is small gamma, and vortex filament has the capital gamma. And when come to here, the vortex filament has the small gamma, and complete vortex sheet strength is capital gamma. Like that, here we assume this is small. Here we assume this vortex filament itself very small.
Okay, sir.
Okay, so each vortex has the small strength. Here, vortex filament itself has the small strength. Is that clear?
Yes, sir.
Okay. So it will be integral 0 to s gamma ds. This equation we will use it in the second unit, where the gamma is the velocity difference. Because mostly we'll take 2D only. Okay. In the 2D case, so what is visible is only these vortices. Okay, these lines are not visible. Okay. So we assume the strength of the complete vortex filament itself small gamma in this aerodynamics. Okay, this is the basics. Then starting vortex. Starting vortex should have easily observed. I have outputs like this. That's not playing. So this is the starting vortex. Simply, if you move the plate due to the pressure difference along the edges of the plate, the vortices are formed. You can see. So if you move the plate, see in the front, the flow hits the surface, right? So you can see my cursor, right?
Yes.
Yes.
So in the front of the plate, we have the stagnation pressure because the flow hits the surface, so high pressure. And behind that, there is no flow. Okay, one simply some recirculating region. So behind the plate, low pressure. In front of the plate, high pressure. Then there is a flow, that is side leakage flow from high pressure to low pressure. That side leakage flow is further rolled up and forms the vortices. Simply that is called starting vortex. This is like a shadow graph technique using the any light source. Here they have taken sun as a light source. We can see the flow pattern. You can see. So the lights are deflected due to the vortex. I think that also should explain. Hmm. This is how the rays are going. The vortices are formed. That vortices deflects the sunlight so that in the center portion there is no light. So we are getting this dark region in the center. This technique is called shadow graph. I will show this video again. Pause it. Okay, that is called starting vortex, and here they explain the same using the airfoil because we are interested in the airfoil only. These vortices anywhere you can observe. Simply, if you wave your hand in the water, you can see the small vortices behind your hand. Or if the door, if you closes, if the floor is dust, you can see the small vortices behind the door. That is called starting vortex. Why it is called starting vortex means it is not, what is it? Immediately it will vanish. Only if you move, that time it will be formed and immediately it will vanish. Here they explain using the aerofoil. So if you move the aerofoil, then there are some pressure difference and vortex are formed. Here because see there is angle of attack, there is a pressure difference. So low side high pressure, upper surface low pressure. Then the flow try to curl around this tip, and this upcoming twisting flow pushing the curl flow rearward, so that here low side we have high pressure, upper surface we have low pressure because the aerofoil is at angle of attack. Okay, what will happen? There will be flow from high pressure to low pressure. Okay, so the flow will try to curl around the trailing edge, and this upcoming twisting flow pushes the curl flow rearward so that it rolled up and forms the starting vortex in the aircraft. Now you can see if you move, we are getting pressure difference and lift, so the starting vortex is formed. Is that clear?
Yes, sir.
And it will vanish immediately, the starting vortex. It will be distorted, then it will be vanished, the starting vortex. This finance. Okay, starting vortex. So assume this aerofoil is at zero lift angle of attack. Okay, so there is no lift, there is no pressure difference. So flow leaves the aerofoil smoothly. And suddenly, if I increase the angle of attack and I am getting some positive lift, then there will be pressure difference. So here high pressure, here low pressure. Due to the pressure difference, we are getting the lift force, and there will be a flow from high pressure to low pressure. So there is a curl around this airfoil. Okay, and this upcoming free stream flow pushes the curl rearward so that it rolled and forms the starting vortex. So this is the physics behind this starting vortex. Okay, so due to the pressure difference, there is a curl flow around the trailing edge, and this free stream flow pushes this downward so that this rolled up and forms the starting vortex. So this free stream also pushes this stagnation point. Suddenly, if you change, you see here is the stagnation point. This free stream flow pushes this stagnation point, also this curl flow. So the curl flow is rolled up and forms it starting vortex. And you can see the movement of trailing stagnation point. Finally, it is in the end. Okay, so the free stream flow pushes both stagnation point to the end, also pushes the curled flow to the rear end as a starting vortex. Is that clear? So
Yes, sir.
whenever you increase the angle of attack, you will observe one starting vortex. For example, from 0 to 2 degree I'm increasing, there will be a sudden increase in sudden change in pressure difference. So there will be one starting vortex, and it will be there for a few seconds, then it will vanish. Okay, because in the real condition the flow is viscous, right? The starting vortex will vanish. And further increasing the angle to 6 degree, again there will be a difference in pressure difference in pressure. So another vortex will be formed, that will be vanished. Okay, like that. For every change in angle of attack, every change in pressure, we will get one starting vortex. This is clear, right? This they will ask in 4 marks. Using this figures, you can explain.
Yes, sir. Clear.
Okay. So next one is Kelvin circulation theorem. So here I have taken one fluid region. Okay, assume flow over the aerofoil. Assume the aerofoil is a symmetrical aerofoil at 0 degree angle of attack. You know this will not produce any lift, right? Symmetrical aerofoil at 0 degree angle of attack. So lift is 0, then circulation also 0. So already I told you, whenever if you want to simulate a lifting flow, okay, whenever you want to simulate the lifting flow, you have to take the vortex. Okay, we have to take the vortex, then only we can simulate the lifting flow. Then the strength of the vortex is capital gamma. Even we have the relation lift is equal to rho v circulation. Okay, so in all the lifting flow derivations, we can see this circulation term, because by including this vortex only, we can simulate the lifting flow. So sometimes instead of lift distribution, they will mention circulation distribution. Both are directly proportional. So here also, if there is a lift, then there will be circulation. Here lift is 0, then the circulation also 0. Okay, this is the first case I have taken. I have taken one fixed fluid region where I am keeping one symmetrical aerofoil at 0 degree angle of attack. It produces same pressure on both sides. So lift is 0, circulation also 0. Okay. Now I am increasing the angle of attack. So you know by increasing that, there will be a pressure difference on lift. Okay, and there will be a starting vortex. So this theorem states, so for the fixed fluid region, that the overall circulation is constant. Okay, for a fixed fluid region, when the circulation is constant, that's what this theorem states. See, same fluid element, it is just stretched. Okay, same fixed fluid element, just stretched because of this angle of attack. So the same aerofoil, same velocity, simply increase the angle of attack. So I'm getting pressure difference and lift here. If there is a lift, then definitely there should be a vortex and with the strength circulation. Okay, so on the aerofoil, I'm having the vortex with the strength gamma 1, and behind that I have the starting vortex with the strength gamma 2. Both are, you see, it is equal and opposite. Okay, so gamma 1, this is minus gamma 2. If you equate, if you add both things, you'll get 0 circulation again. Okay, so for fixed fluid region, the circulation is constant. That they, even if you change the angle of attack, even if you wait for many more times, it is constant. So they mention as time rate of change of circulation is 0. Okay, so Kelvin theorem states time rate of change of circulation for a fixed fluid region is 0. Is that clear?
Sir, sir, fixed fluid region means like in between two fixed streamlines.
No, whatever the control volume I have taken, that is fixed.
Okay, okay, sir, okay.
Okay. So fluid region means here I am mentioning the control volume. For a particular control volume, okay, for a particular control volume, the circulation is constant. So inside, many things can happen. Angle of attack can be increased, decreased, anything can happen, but the overall circulation will be constant. If it is 0, here also it will be 0. Okay, so here positive gamma, here negative gamma, overall gamma is 0. Okay, so here the starting vortices. See here on circulation, positive gamma. Here starting vortex, negative gamma. Overall it is 0. And this is another case. So I will explain using the video. So this is starting vortex. So above the airfoil, we have some circulation. And starting vortex has another circulation. Both are equal and opposite. Okay, so here and here, equal and opposite circulation. So the total control volume circulation will be 0. Okay, now same control volume, same aerofoil. So instead of continuously moving it, I just stopped. Actually, initially it is stationary. I just moved. See, it is at angle of attack. So there is a pressure difference. It is at angle of attack. Due to the pressure difference, the starting vortex is created, but suddenly you stop the control, that is aerofoil. That means there is no pressure difference on the aerofoil. Then there should be equal and opposite circulation, right? Then only the domain control volume circulation will be constant. So what happened? There is another one vortexes formed, which is opposite and equal. Now also, if you see the control complete the total circulation, it will be 0 only. This is positive, this is negative, again it will be 0. Like that, different examples are there for this Kelvin circulation theorem. Is that clear?
Yes, sir.
So in the exam, they ask you outright time rate of change of time rate of change of circulation for the fixed fluid region is 0, or circulation is constant for the fixed fluid region. Like that, you have to write it. You can use this example. Sometimes they will ask, so explain the Kelvin circulation theory using the proper example. You can explain using this starting vortex. Here there is no lift, circulation is 0. Here there is a lift, but there is a starting vortex. So again, the overall circulation is 0. Like that, using this example, you have to explain. So next one is Kuta condition. So this is a scientist
So
name.
can you go on the previous slide?
So here on circulation, here on circulation. This is positive, this is negative. So overall it is 0. Here I just stopped moving this aerofoil. So there is no pressure difference, there is no lift. So here two vortices are formed. This is positive, this is negative. So overall it is 0. Okay. If I keep on moving, these vortices will not exist. Then it will be like a starting vortex. I just stop. So there is another vortices. Okay.
Yes, sir.
Okay. Then Kuta condition. So Kuta is a scientist name. So this profile you have studied flow over the rotating cylinder. Some students are continuously messaging. Okay. Number 3. Okay. So for stationary cylinder, these are the stagnation point, and we will get only one streamline pattern. Okay. This is one case. Then for rotating cylinder, depends upon the vortex you have taken, we will get different streamline pattern, different stagnation points. So we don't know which result we have to take it. Okay, stationary cylinder, we have only one result using the potential theory. But if you take the rotating cylinder, it gives n number of results. Circulation less than 4 pi AU, equal to 4 pi AU, greater than 4 pi AU, like that. It will give n number of results. So we don't know which result we have to take it. The same issue will be there if you take aerofoil also. So to rectify that, we are using this Kuta condition. So here are the statements of Kuta condition. So he has done some experiment and he made some observations that he summarized. So his first observation is flow leaves the trailing edge of the aerofoil smoothly. Okay, flow leaves the trailing edge of the aerofoil smoothly, but you know this is applicable only to the thin object at small angle of attack. Okay, if it is thick, definitely flow will separate, or if it is at high angle of attack, definitely flow will separate. we cannot say the flow leaves the tail image smoothly. Okay, so this observation is again with lot of assumptions. Flow leaves the tail image smoothly. It is applicable only to the thin object with a small angle of attack. Here also you can see there is a small separation, right? Is that clear? First point.
Yes.
Okay, so this is his first point. Then once the flow leaves the tail image smoothly, then that point will be the stagnation point. Okay, so here I have seen, right? If the flow leaves the tail image smoothly, then this point will be the stagnation point. Okay, this is forward stagnation, this is rearward stagnation. Okay, so the second point is if the flow leaves tail image smoothly, then the tail image point will be the stagnation point. That is the second statement. The third statement, so strength of the vortex at the stagnation point is 0. Should I explain? I already told you in direct method, we will place the vortex sheet or source sheet over the airfoil. Okay, that is small vortexes will be placed. So strength of the vortex and the trailing edge will be 0 because so in the vortex sheet we are considering the infinitesimally small vortices. So it is acting like a rotating fluid element where the strength is like a vorticity, simply the velocity difference. Okay, so if this trailing edge point is the stagnation point and the velocity at this point is 0, so both velocities are 0, then the strength also will be 0. This is his third statement. The flow leaves the trailing edge smoothly, then this point will be the stagnation point. That means velocity will be 0. That means strength at that point also 0. Is that clear?
Yes, sir.
Okay. So this is the special case. This is the normal case for finite angle. If this is the stagnation point, velocity is 0. So the strength of the vortices at that point is 0. And this is the special case. Cusped trailing edge. That means the waning moon, waxing moon you see, right? But this sharp edges is called cusp. Okay, waning or waxing moon, the sharp edges is called cusp. The same type of sharp edges we can see if you take the thin objects. That is, if you take the thin flat plate, then this edge is looking like a cusp. Okay, so if you take a thin flat plate, then we cannot say this point is a stagnation point because flow will be equal. Okay, if it is curved or some angle will be there, means here flow will be accelerated, here flow will be decelerated, there will be some difference. But if it is a flat plate, thin flat plate, both sides, the velocity will be same only. Okay, so for this thin flat plate, we cannot say this is the stagnation point or the velocity is 0. So this is special case. Velocity will be equal on both sides. And here also the third condition will be applicable because both velocities are equal. So VU minus VL will be 0. Okay, this is a special case. So three statement. First one is flow leaves the trailing edge smoothly. But again, this is with lot of assumptions. And once the flow leaves the trailing edge smoothly, that means this point is a stagnation point. And if it is a stagnation point, that means velocity is 0 means strength also will be 0. Strength of the vortex also will be 0. This is his third point. But this is the special case. Cusped trailing edge, that is for a thin flat plate. Velocities are equal, but still the strength of the vortex is 0. Equivalent velocity, but here also the strength is 0. Okay, V1 minus V2, again you will get the same last point, circulation, that is strength at the trailing edge will be 0. And main use of this Kutta condition is, if you don't use the Kutta condition, the potential theory will give you n number of results. We don't know which one you have to pick. So using the Kutta condition only, we can get the proper solutions. Otherwise, it will produce n number of solutions. What is the sound? Okay, recording started. Thank you. 89 has done. The next one is Helmholtz theorem. This also asked in 4 marks or sometimes 6 marks. So the first point is If you take a flow field, and the particle may undergo translation, rotation, and distortion. Okay, translation means simply moving, and rotation means the particle may rotate, and distortion, the shape itself will vary. Okay, here it is rectangle, here it is distorted. Okay, so in every flow field, the particle may undergo any one of this motion or combination of these three. Okay, for example, if you take irrotational, we observe it is only translation. If it is rotational, we observe both translation and rotation. Maybe if you take flow through the nozzle, where the flow is compressed, you may observe this distortion also, like that. So all the flow field will have combination of these three motions. This is his first observation. Is that clear? Fluid particle may undergo translation, rotation, and distortion. So any combination may happen, depends upon the flow condition. This is the first point. Then second point, already discussed, that is strength of the vortex filament is constant. Okay. So vortex line or vortex filament, the strength is constant because we have taken inviscid. So the strength will not decrease. So strength of this vortex filament is constant. If the strength of this vortex filament is constant, then it will not end in a fluid. Okay, only if the strength is not constant, up to certain distance it can extend, then it will disappear. But as the strength is constant, it will not disappear, so it will not end in a fluid. Okay, and if it is not end in a fluid, then the other possibilities are it should extend to the infinity distance. Okay, so it cannot end in a fluid. If it is not ending in a fluid, then it should be extend to the infinity distance, or it can form the closed loop. Okay, in that case, we can maintain the same strength, or it may terminate if there is a discontinuity. This will explain. So first 4 points are clear, right? The strength is constant. If it is constant, it cannot end in a fluid. If it is not ending in a fluid, it should be extended to the infinity distance, or it must form the closed loop. Is that clear?
Yes, sir.
The last point, it may terminate if there is a discontinuity. I think using this video, you can explain that easily. So this is also one vortex filament. You can see, using the dye, we can see the vortex filament within the water. And you see, below that we have the water, above that we have the air. There is a discontinuity in the medium, so that the vortex filaments are terminated here. Okay, from here to here. Yeah, it is formed only from here to here. It couldn't extend on the upper surface because there is a different medium. Is that clear? So if there is a discontinuity, it may terminate. Is that clear? Last point. So here there is a discontinuity of medium, air and water. So it is formed within the water, so it couldn't extend to the air. So it terminates due to the discontinuity in the medium. It is his fourth point. Is that clear?
Yes, sir.
Okay, same. That's it. Yeah, this is his 5 observation, 4 marks or 6 marks. So the fluid particle may undergo translation, rotation, distortion, and strength of the vortex filament is constant. If it is constant, it cannot end in a fluid. Then other possibilities, it has to extend to the infinity, or it must form the closed loop, or it will terminate if there is a discontinuity in the medium. This is the Helmholtz theorem. So next one is lift distribution. So if you take the infinite wing, it is where the cord is extended to the, that is span is extended to the infinity distance, then you will get uniform lift distribution. Okay, so this is equal to the aerofoil lift distribution. So there is no edges, that is wing tips. So we will get the uniform lift distribution. But if you take the finite wing, 3D wing, you know there will be a wing tip vortices, side leakage flow, etc. and all. So this side leakage flow reduces the pressure difference near the tip region. So instead of straight line, the lift distribution is decreased. So infinite wing, it is constant. But for the finite wing, due to this side leakage flow and wing tip vortices, there is a loss of pressure difference and lift. So we are getting this curved lift distribution. This is the difference between infinite wing and finite wing lift distribution. So this is how it will vary. So in the center it is maximum, and towards the tip it will decreasing. At last it will be zero because there is no pressure difference. So like that it will vary. Is it clear? Lift distribution for infinite wing and finite wing.
Yes, sir.
Okay. So if you take flow over the wing, so there will be a lift distribution, and there will be a side leakage flow, and there will be a wing tip vortices. Okay, so these three things will be there: so lift distribution, side leakage flow, and wing tip vortices. So these three phenomena we have to simulate it using the mathematical expression in the aerodynamics and the aerodynamics. Okay, so flow actually using the aerodynamic one derivation, you cannot find the drag. All those aerodynamic derivations, whatever you are studying in the aerodynamics one, it will be useful only to simulate the lift. Drag cannot be predicted. So we are going to simulate lift distribution, side leakage flow, and this wing tip vortices. These three we are going to simulate it. For that, we are taking one hypothetical arrangement, vortex sheet arrangement. Already I told you, whenever if you want to simulate the lifting flow, we have to take the vortex sheet arrangement, right? Vortex sheet means n number of vortex filaments. So vortex sheet arrangement you have to take it. Here also they are taking one arrangement, vortex filament arrangement, and the shape is looking like the horseshoe. So they are calling this as horseshoe vortex. This is a hypothetical arrangement. So how they are taking? They are taking varying span vortex filament. See, the span is varying. Okay. So the varying span vortex filament with the ends are turned backward. Okay, it is not extended like this. The ends are turned backward. This type of hypothetical vortex filament arrangement they are taking to simulate these three phenomena: lift distribution, side leakage flow, and wing tip vortices. Okay, so it is a hypothetical vortex filament arrangement. So varying span vortex filament with the insert turned backward. Is that clear?
Sir, so the strength is constant for all the
Yeah, strength
filament?
is constant. Strength is constant. Always strength is constant. Vortex filament means aerodynamics one. Any other doubt? So in the 4 mark, if they ask horseshoe vortex, you have to write it is a hypothetical vortex filament arrangement to simulate lift distribution, side leakage flow, and wing tip vortices, and it has varying span. You can see this is different span, this is a different span, this is a different span, this is a different span. Okay, so varying span vortex filament with the ends are turned backward. So you have to explain about this arrangement, and you have to explain this is used to simulate these three things. Then you will get 4 marks for horseshoe vortex. And so this is the vortex sheet. You can see by this arrangement itself, you can see this will easily simulate the side leakage flow and the wing tip vortices. So everywhere the vortex is going like this. So by seeing itself, we can understand this vortex filament arrangement can simulate side leakage flow, also the wingtip vortices. Okay, so these two conditions are satisfied by observing itself. Now I'll explain how it simulates the lift distribution. Same thing they explain. So the wingtip, the vortex filament arrangement simulates side leakage flow, also the wingtip vortices. Now we will see how it simulates the lift generation. So here I have taken 4 vortex filaments. Actually, for better results, you have to take more number of vortex filaments, maybe infinite number of vortex filaments. If you take, you can get the proper lift distribution. Okay, but here I have taken only 4 so that you can easily visualize. So each vortex filament has the same strength gamma and it is constant. Okay, so now I am going to find the circulation distribution, because circulation is directly proportional to the lift. In the aerodynamics, so instead of lift distribution, they will give circulation distribution because both are proportional, directly proportional. So here also, instead of lift distribution, we are drawing circulation distribution. Assume I am going to find the circulation distribution at these locations, that is along this span. So in the center line, if you take 4 vortex filaments are crossing. Okay, so the strength is 4 gamma. Maybe the point is here. And this line, if you take, only 3 vortex filaments are crossing. So this is 3 gamma. Then third line, if you take, only 2 vortex filaments are crossing. So here the strength is 2 gamma. And this line, only vortex filament is constant. So it is 1 gamma. Like that, if you join this point, you will get this type of circulation distribution. Similarly, other side also you will get the same. I have taken only 4, so I am getting these steps. But if you take infinite vortex filaments, you will get this curved shape properly. Is it clear? Why we are taking varying span vortex filament? Okay. So by using this varying span vortex filament, we can simulate the lift distribution on the finite wing. So this arrangement gives simulation of side leakage flow, wingtip vortices, also the lift distribution on the finite wing. So this arrangement is called horseshoe vortex. Actually, this is called bound vortex. Without this extension, it is called bound vortex. So bound vortex may simulate only the side leakage flow and the lift generation. It cannot simulate the wingtip vortices. So horseshoe vortex means that can simulate both tip vortices, side leakage flow, lift distribution. But bound vortex is the vortex filament only on the wing portion we are taking, so it can simulate only the side leakage flow and the lift generation. Okay, both can be asked, bound vortex or horseshoe vortex. Don't write horseshoe vortex in the bound vortex. Okay, so horseshoe vortex is the complete vortex formation, and bound vortex is vortex filament arrangement only on the wing. Yeah, that's it. Some basic theorems are over. Any doubt? Horseshoe vortex, bound vortex, lift
So in
distribution.
bound vortex, what can't we find?
So the bound vortex, the extensions are cancelled. So we cannot simulate the tip vortices. In the bound vortex, we are taking only the wing portion. So we are not taking this rear portion. So horseshoe vortex is the combination of bound vortex plus this wingtip vortex. Okay, so the overall wing arrangement is horseshoe vortex, and only on the wing if you take the vortex filament arrangement, that is called bound vortex. Is that clear?
Yes, sir.
Okay. So as I mentioned, the vortex strength is constant and it will extend to infinity distance. You can see here. So this is the lift generation. This is the side leakage flow. This is the wingtip vortices. And while starting, there should be the starting vortex, right? So theoretically, if you say, it will be somewhere here, the starting vortex. That's why we are getting this closed loop. Okay, in the practical, what will the starting vortex will vanish immediately. Okay, but in the theoretically, it has constant strength, so it will not vanish. Even assume, how to explain that? Okay, in the real condition, if you take air graph, just if you change the angle of attack, there will be a starting vortex and it will be vanished. But in the real condition, in the theoretical condition, as the strength is constant, as the flow is inviscid, even the aircraft leaves the airport, there will be a starting vortex still in the airport. Like that, theoretically, we are assuming. So in this case, that also you can include. So lift generation, side leakage flow, ring tip vortices. We can take that starting vortex also, then we are getting this closed loop. Is that clear?
Yes, sir.
Okay. The next one is Kota-Joukowski theorem, where we are relating lift is equal to lift with with circulation. This is a 12 mark or 8 mark question. So, for example, I have taken flow over the aerofoil. I already told you in the aerodynamics one, we are not taking the thick aerofoil. We are taking a thin aerofoil where the upper surface and lower surface coincide on the camber line, and the camber also very small. This is all the assumption we are taking. So this is our final aerofoil, only the camber line. And to simulate, we have to take uniform flow plus vortex sheet because this is a lifting flow. So this is the vortex sheet. Using that, you can simulate lifting flow over the aerofoil. Okay, so free stream properties are pressure P infinity, density rho infinity, velocity V infinity, and the length varies from 0 to S. And you know that free stream velocity is V infinity, and the vortex sheet has the small strength. So upper surface it is on the positive direction, lower surface it is on the negative direction. Okay, so upper surface I am taking plus dV, lower surface I am taking minus dV. Okay, because vortex will have tangential velocity, both are opposite direction. So this is positive, this is negative I have taken. So free stream is V infinity, vortex heat velocity is dV, then the overall velocity on the upper surface is V infinity plus dV, and overall velocity in the lower surface is V infinity minus dV. Okay, assume I am finding this in the small region ds, that's why I have taken the small dV. So on this ds, velocity is higher on the upper surface, velocity is lower on the lower surface. So velocity is high, and the pressure will be less. Here velocity is less, so pressure will be high. So I am getting the pressure difference PL minus PU. Because of the pressure difference, I am getting this lift. I just repeat. So I am placing the vortex sheet. So vortex sheet induces the velocity difference. So this is the upper surface velocity, higher velocity. This is the lower surface velocity, lower velocity. So we are simulating velocity difference. Then this will give you the pressure difference also. Upper surface low pressure, lower surface high pressure. Due to this pressure difference, we are getting the lift. So whatever I am finding is only for this small section. So the dl is equal to PL minus PU into ds on this small section. Now if you find the lift of this complete aerofoil, simply we have to integrate from 0 to S. Is that clear?
Yes, sir.
Okay. Now this is our lift equation for the complete aerofoil. In terms of pressure difference, I mentioned pressure into area. Now we have to find this circulation equation. So circulation equation already we derived for the vortex sheet. So here I have taken. So for this small distance ds, the strength is d gamma, where it is gamma into ds. Then for the complete vortex sheet, we have to integrate from 0 to s. Okay, so gamma into ds, where the gamma is just the velocity difference, because we assume the vortex is very small, so it is equal to the rotating fluid element. Okay, so this formula already we discussed. Same thing I'm taking here. For the small section ds, this is the strength. Then for the complete vortex sheet, this is the strength. Okay, and where the small gamma is the velocity difference, upper surface velocity and lower surface velocity. We know the upper surface velocity and the lower surface velocity. So upper surface it is v infinity plus dv, lower surface it is v infinity minus dv. Substitute, simplify, you will get this circulation equation for this aerofoil. Is that clear?
Yes, sir.
So now I got two equations, lift equation in terms of pressure, circulation equation in terms of velocity. I have to equate these two equations so that I can compare lift with the circulation. But here it is in terms of pressure, here it is in terms of velocity. So we know one basic equation which relates pressure and velocity, that is Bernoulli's equation, where P plus half rho v square is equal to constant. So apply that on upper and lower surface. First lower surface, if we take PL plus half rho v square, then upper surface PU plus half rho v square, then rearrange because we need PL minus PU, rearrange and simplify, we are getting PL minus PU is 2 rho v infinity del v. Get these steps, you can check it at a simple rearrangement only. So to equate lift and circulation, I have to relate this pressure and velocity. So I am taking Bernoulli's equation, apply to the lower surface and upper surface, simplify, you will get this equation. Okay, so this is lift equation, this is circulation equation, and we found PL minus PU is this much. Then substitute in this lift equation. This is the final lift equation. Okay, instead of PL minus PU, we have taken this 2 rho v infinity del v, and this 2 rho v, everything is the constant because we are not changing the free stream flow property. Density is same, velocity also same, 2 also constant. So I'm going to rearrange this equation. Simply I'm taking this rho and v outside. Remaining is integral 2 del v del s ds, which is equal to the circulation. So I can write L dash is equal to rho v gamma.